So in class, I had you convert the substrate to micromole per liter, but you actually don't have to do that. I'm going to go through the math to explain why you don't. You can just keep the units as they are, and that saves you a step. So the substrate, 1 over the substrate concentration becomes your x value, so you just take 1 over all of these numbers. And then the y values are 1 over v naught. So you just take 1 over all of these numbers to get to your y values. And then when you enter the data in Excel and generate a scatter plot and then get the trend line from that, you can display the equation on the chart which is shown. So the equation y equals 0.0024x plus 0.0017 represents this equation. 1 over v naught equals km over v max times 1 over the substrate concentration plus 1 over v max. So this is your y-intercept, so that corresponds to that number. And this would be your slope, which corresponds to the 0.0024. And notice the only difference between this equation and what we did in class is that the slope differs by a factor of 1,000 because we didn't convert here the millimoles to micromoles. So the 1 over V max equals 0.0017, and V max is in units of micromoles per minute. So we get V max equaling 588 micromoles per minute. Now we just have to solve for Km. So Km over V max is the slope. So 0.0024. Now the units for the slope would be the units for Km over V max. So the units for Km would be millimole per liter, since that is the concentration units we used for the substrate, divided by micromoles per minute, because those are the units we used for the velocity. So that's going to equal Km over V max, and we just solved for V max, so that equals Km over 588 micromoles per minute. Now I just rearrange the equation, so I get 0.0024 millimoles per liter divided by micromoles per minute times 588 micromoles per minute equals Km. So here the units cancel out. And since the units cancel out for velocity, you don't actually have to go through the additional step of making sure the substrate and the velocity units equal. It doesn't hurt to do that because sometimes it does matter, but in this case it doesn't. And then you get a Km value of 1.411, and then the units would be millimole per liter. So in this question, I also had you convert everything to the same unit, which is fine, it always works, but you can do the trick where you just keep everything as is because they will cancel out appropriately. So let me explain. So V naught is going to equal the V max, which is 1.2 molar per second, times the substrate concentration, which is 3 micromolar, divided by the Km, which is 10 micromolar, plus the substrate, which is 3 micromolar. So that gives me 1.2 molar per second times 3 micromolar divided by 13 micromolar. So here notice the micromolar units cancel out. That's why you don't actually have to go through that extra step of converting all the units to the same units. So 1.2 times 3 divided by 13, and I get 0.28 molar per second. And we do the same thing with B. Divide by 10 micromolar plus 7 micromolar equals 1.2 molar per second times 7 micromolar divided by 17 micromolar. Notice here again the units cancel out, and I get 0.49 molar per second. And then the last one follows the same logic. So 1.2 molar per second times 25 micromolar divided by 10 micromolar plus 25 micromolar equals 1.2 molar per second times 25 micromolar divided by 35 micromolar. Again, the micromolar units cancel out, and then I get 0.86 molar per second. In question number 3, I give you two enzymes, a wild type and a mutant. So wild type just means that which naturally exists. And then here are the Km values and the Vmax values. So the first question is, which enzyme has a higher affinity for the substrate? Here you can assume that Km is related to binding affinity in a manner similar to Kd, which is definitely not always the case. So if that's true, then we know the smaller the Kd, the greater the binding affinity. So the mutant would be the one with the higher binding affinity. Then B is, what is the initial velocity of the reaction catalyzed by the wild type at a substrate concentration of 10 millimolar? So here I'm going to use that equation. V naught equals V max times substrate divided by Km plus S. So again, I don't have to actually convert the units because they're going to cancel out. So micromole per minute, that's the Vmax times the substrate of 10 millimolar divided by the Km, which is 10 millimolar, plus the substrate, which is 10 millimolar. And notice the millimolars are going to cancel out, and you end up with 50 micromoles per minute. Then C, what is the kcat when the total concentration is 0.33 nanomolar? Now here, you do need to switch the units. So kcat is going to be equal to the Vmax of the mutant, which is 1 micromole per minute, divided by the enzyme total, which is 0.33 nanomolar. So kcat, the unit for kcat will just be per minute. So you need to actually cancel out the micromole and the nanomole. So to do that, you have to make them equal. And when you convert the nanomole to micromole, you get 1 micromole per minute divided by 0.00033 micromole equals 3030 per minute. So based on the information shown in this problem, which isozyme has a higher affinity for acetaldehyde? So if the isozyme in sensitive people allows for a higher concentration of this aldehyde to build up, that means that in sensitive people, the ALDH enzyme is not as active. It doesn't have as high an affinity for acetaldehyde as the normal isozyme. And because it doesn't have as high of an affinity, this will build up in a person's system, causing flushing. Therefore, the isozyme that has the higher affinity would just be the normal ALDH enzyme. because if you had a high affinity, if you were an enzyme with high affinity, you wouldn't allow the substrate just to sit around. You would immediately want to bind to it and start converting it to, in this case, acetic acid. So the next question involved toxicity of methanol. So in this, you can oxidize methanol to formaldehyde, which is toxic, which then further gets oxidized to formic acid, which is also super toxic. However, there is a drug called famotidine, which can inhibit the conversion of methanol to formaldehyde. So the question is, how would this work to treat methanol poisoning, and what do you think would happen to the methanol? So it would stop the conversion of methanol to formaldehyde, and then if that doesn't happen, then it won't be further converted to formic acid, and then the methanol would just be excreted. As methanol. Okay, in this problem, I'm giving you velocity data and substrate concentration data for the enzyme alcohol dehydrogenase with and without the inhibitor famotidine. So you need to use Excel and complete a Lineweaver-Burke plot to evaluate the kinetics with and without the inhibitor, and then from that figure out if this is, what type of inhibitor this is, competitive, uncompetitive, mixed. So this is the result of doing that. So remember, in this, the x-axis is going to be 1 over the substrate, and the y-axis is going to be 1 over V naught. And here I just used the units as they are, which actually happen to all be the same anyway. So I get this equation for series 2, which is with the inhibitor, and this equation for series 1 without the inhibitor. So now determine the values of Km and Vmax for each line with and without famotidine. Are they different? And that's going to tell us about the type of inhibition that famotidine enacts. So notice that the y-intercept is essentially the same. So for Vmax, 1 over Vmax is equal to the y-intercept. So 1 over Vmax would be equal to 0.0177 for the series 1, the line in blue without the inhibitor. So Vmax is equal to, let's call it 57 millimolar per minute. And if I use the slightly different y-intercept, Vmax equals still, if I round them, they end up being the same. So that's my Vmax. Now I just have to figure out my Km. So for series 1 without the inhibitor, the slope is 0.0058 equals Km over Vmax, which is going to equal 0.33 millimolar. When I do the same equation with the other line, I get 0.0109 equals Km over the same Vmax, which equals 0.62 millimolar. So there's a twofold difference of the Km between the series 1 and series 2 lines. So now determine the values of alpha and alpha prime for the inhibitor. So alpha would be the ratio of the slopes, and then alpha prime would be the ratio of the intercepts. So since the y-intercepts are essentially the same, the alpha prime is equal to 1. And then the alpha would be equal to the ratios of the slopes, which would be 2. or you could think of it as the apparent Km is equal to alpha Km. And here the apparent Km for the series with the inhibitor was 2 times the Km of the line without the inhibitor. So then, based on this information, is famotidine competitive, uncompetitive, or a mixed inhibitor? So here are the things you need to know. For competitive, there's no change in Vmax, but an apparent increase in Km with the inhibitor, and the lines intersect at the y-axis. So this I didn't have these go all the way to the y-axis, but you can, in Excel, have it forecast data points so that it will extrapolate the lines. But another way of saying that they intersect at the y-axis is that they basically have the same y-intercepts. So that would be the case here, that they intersect at the y-axis because they have the same y-intercepts. So it looks like it's competitive. Now, uncompetitive, we would see that the lines would be parallel and they would not intersect, and there would be an apparent decrease in Km, and we saw an increase in Km, and there would be no change in the slope, and we did see a change in the slope. With mixed inhibition, the lines intersect left from the y-axis, and we would have seen a decrease in Vmax, which we did not see, and we would see a change in Km. So as a result, we can say that this is competitive inhibition. So the final thing I want to talk about are some of the enzyme mechanisms. So chymotrypsin is something that helps to digest proteins by breaking peptide bonds. And this mechanism has been extensively studied, so we know a whole lot about it. So what happens is you have these important amino acids in the enzyme in the active site that are going to be participating in the mechanism. So we have this hydrophobic pocket and something called an oxyanion hole. So here's our substrate, it's some polypeptide. So the polypeptide is going to fit into the active site. And when it does that, that's where we have now the enzyme substrate complex. And that's going to position everything for the next steps. So in this first step, the histidine 57 is going to grab a hydrogen off of serine, which allows it to then do a nucleophilic attack on the carbonyl carbon of the peptide, breaking that pi bond, and those 2 electrons go on to the oxygen atom. So now you have this complex where this oxygen has a negative charge and the histidine nitrogen has that red hydrogen on it. So this is an intermediate, and it is a short-lived intermediate. Now that negative charge that you created on the oxygen here is stabilized through hydrogen bonds and what we call the oxyanion hole. So it's stabilized by the hydrogens on this glycine residue and this serine residue. So that tetrahedral intermediate then collapses, so it reforms the carbonyl double bond and it breaks the CN bond, which then gets protonated by the hydrogen on the histidine as shown. So by doing that, we've cleaved that carbon-nitrogen bond of the peptide. So now we have this intermediate acyl enzyme intermediate. So notice that we've got a covalent bond. So this is covalent catalysis mixed with acid-base catalysis. So we've got a covalent bond here with the enzyme, and that oxygen is from the serine that's now connected to the substrate. So then water is going to come in, and water is going to attack the carbonyl carbon of the substrate, and that's going to be assisted by this histidine, which is going to act as a base. So that's that base catalysis, grabbing a hydrogen of water, allowing a hydroxide essentially to form, which then does nucleophilic attack on the carbonyl. And then again, we break that pi bond and those electrons go onto the oxygen, again forming a negative charge that is stabilized in the oxyanion hole. Now this again is really just showing the water attacking that we just saw in the last slide. But then we get to this tetrahedral intermediate, which then again collapses. So now we've got a carboxylic acid here, which will leave from the enzyme, and that leaves behind the enzyme as it was originally. And then finally the product leaves and dissociates. So the easiest question on this slide to answer is, why does chymotrypsin lose its activity at pH 5? And the reason is that histidine residue, this nitrogen here, needs to act as a base in the mechanism. If you look back at the mechanism, it is taking a proton away from the serine so that serine can then perform a nucleophilic attack. So at low pH, that histidine is going to be protonated on that nitrogen, and that nitrogen's protonated, it's not going to be able to be a base. Because to be a base, you need either a pi bond or you need a lone pair, and histidine is going to use that lone pair to grab an H from serine. And if the histidine is protonated, which it would be at low pH, then that can't happen. So if that's protonated, it cannot act as a base in the mechanism. Now the more complicated question is this first one. So mutant chymotrypsin A has an asparagine near the active site instead of an aspartate. How does this affect the enzyme's activity? And the answer is that it again affects the histidine. So the serine, this hydrogen, is not very acidic, and the histidine generally would have a difficult time removing it with base catalysis. However, when we have an aspartate, there's something called a catalytic triad that forms. And essentially, there's a hydrogen bond that forms between this O- and the hydrogen on histidine, which pumps up the ability of histidine to act as a base to then deprotonate the hydrogen on serine. And without that catalytic triad, so in the mutant with asparagine, that effect isn't seen. Therefore, the mutant would have lower enzyme activity. The final mechanism is that of a lysozyme. Lysozymes cleave cell walls of bacteria. And this mechanism involves two successive SN2 steps. So in the first step, aspartate residue 52 attacks the anomeric carbon of that sugar, breaking the glycosidic bond, and the two electrons in that bond grab a hydrogen from glutamate 35. So then you get this first product released, and you're left with the deprotonated glutamate 35, and you've formed a covalent bond. Next, water gets involved. So here the glutamate that's now negatively charged deprotonates the water to make it a good nucleophile. So now you've basically got hydroxide, which is going to attack the anomeric carbon, kicking off the aspartate that added in the first step. And now you have your second product. So notice that the glutamate here is acting as a general base catalyst. So if you're grabbing hydrogens, you're a base catalyst. If you're providing hydrogens, you're an acid catalyst. And a lot of times both things are happening. So a lot of times we see both acid and base catalysis. And that's it for this video. Thank you.